to Friday Happy Math Hour. This week, I'm going to go over basic concepts of probabilities, permutations, and combinations. These are the topics that I'm going to cover today. Introduction to probabilities, basic concepts of probabilities, multiplication principle, permutations, and combinations. Okay, first of all, this is from section 8.2, Introduction to Probabilities. We need to know some of the some of the vocabulary in order so we can know what they're asking for. So, for example, random experiment is a process by which we observe something uncertain. After the experiment, the results of the random experiment is known. The sample space is denoted by S. S means sample space, the set of all possible outcomes of a random experiment. Okay, these are examples of sample space. For a coin flipping, the sample space is heads or tails, right? Because when we flip a coin, it can only be a heads or it can be a tails. That's why the S equals to sample space is heads or tails, and they put it in set block notation. The next one is rolling a fair die. By a fair die, they means because at times some of the dice are loaded. By loaded, it means that every time that you toss or that you roll a die, it goes to a certain number. So rolling a fair die means that every side has the same weight. So that's why every side has an equal opportunity to land on that number. So for the fair die, the sample space, it can be a 1, a 2, a 3, a 4, a 5, or a 6. So these are examples of sample space. To find the sample space of an experiment, at times it is easier to draw a tree diagram. What do I mean by a tree diagram? Okay, I'm going to show you what I mean by a tree diagram. So for example, find the sample space of flipping a coin twice. Okay, so my first flip, it can be heads, right? Or it can be tails. This is my first flip. My second flip, right? It can be heads or tails again. Or if my first flip is tails, then it can be heads and tails. So my sample space is seen by following the diagram here. You see it can be heads, heads. It can be heads, tails. It can be tails, heads. And it can be tails, tails. So these are the possible outcomes for flipping a coin twice. So this is my sample space. My sample space is heads, 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 tails, tails, heads, and tails, tails. That's considered my sample space. Okay. An event. An event is an outcome or set of outcomes of a random experiment. Okay. An event is a subset of a sample space. For example, if the sample space of flipping a coin is heads, tails, then one event can be heads, right? That's one event, or another event can be tails. But this example, for it to be heads, which represents the outcome of heads, when it's H, that means that the event is heads. Checkpoint, okay? Suppose a die is tossed. Write the given events in set notation. The number shown is less than 3, right? So for the solution, this is my sample space. It can be a 1, 2, 3, 4, 5, 6, right? But for the event to be less than 3, it can be a 1 or it can be a 2. And that's it, right? Because less than 3 means that 3 is not included. So this is the set notation of the event showing a number less than 3 from tossing a die. Now for B part, the number showing is a 5, right? So that's very basic, so it's just 5. For C part, the number showing is an 8. It's going to be empty set because a die can only be 1 through 6, not an 8. So there's no way you can get an 8. The number showing is even, right? So even, it can be a 2, a 4, a 6. So this is the event. Okay, a sample of an event. Okay, now, all this is leading to basic probability principles. And here's the definition. Let S be the sample space of an equally likely outcome. and let the event E be a subset of S. Then the probability that the event E occurs is the probability of E is equal to N of E over N of S. N of E is a number of elements in E, and N of S is a number of elements in S. Okay? By this definition, the probability of an event is a number that indicates the relative likelihood of the event. And again, this is what I just said earlier. N of E is a number of elements in the event. N of S is a number of elements in the sample space. Checkpoint. Suppose a single fair die is rolled with a sample space S equals to 1, 2, 3, 4, 5, 6. Give the probability of each of the following events. So for A part, the die shows an even number. Okay? So this is the set, right, of an even number. It's going to be a 2, 4, 6, which is 3, right? 3 elements. And the sample space is going to be 6, right? Because there's 6 total elements. So the event, the probability of the event, right, that's an even number, is going to be 3 over 6, which is 1/2. So my answer is 1/2. Let's try B. The die shows a number less than 10. So for the event less than 10 is going to be every number, right? It's going to be 1, 2, 3, 4, 5, 6, every number in the sample space. So for the event, and the sample space is 6, and the number of the event is 6. So for the event F, which means that is going to be the die shows a number less than 10, is going to be 6 out of 6, which is equal to 1. So the answer is 1. For C part, the die shows an 8, right? There's no way, right? So there's no 8, right? So there's none. So 0 elements for N of E. And N of S is equal to 6. So the probability of the die shows an 8, which is event G, is equal to 0 over 6, which is 0. There's no way you can get an 8. So it's 0. Okay. Hey guys, before I continue, are you guys okay? If you guys are okay, please raise your hand up. If you guys feel that you're understanding the material. Miss Patricia, if anybody has a question on the chat, please let me know what it is, okay? Because I don't have my other computer. I just have this one. Yes. So if somebody raises your hand up, let me know, right? And that way I can answer the question. Okay, now this is another checkpoint. A single playing card is drawn at random from an ordinary 52 card deck. Find the probability of drawing a queen, which is part A. Part B is a diamond. Part C is a red card. And part D is a face card or an ace. Every time that I teach this course, I like to bring real playing cards to class. Okay, so in this PowerPoint, I try to make it as close as being in lecture class as possible. So for example, right, so this this is like a deck of cards. For the people that don't know how to play cards or they don't know about cards, there's 13 there's 4 suits with 13 cards in each suit. For example, the ace, they have a 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you have a jack, a queen, and a king. If you notice, they all have the same numbers but different suit. This is called the clubs, the spades, the hearts, and the diamonds. And there's 13 on each one. 13 clubs, 13 spades, 13 hearts, and 13 diamonds. A total of 52, right? That's what it means by a 52 card deck. Okay, now, there's 26 black cards and 26 red cards. And there's one of the face cards. Hey guys, the face cards are the cards that have a face on them. For example, you see the jack has a face, the queen and the king, these are all called face cards. And I just got the ones from the spades, but there's three face cards on each suit. You see there's 3 clubs, the king, queen, jack. There's 3 spades, what I have here at the bottom. There's 3 hearts, the king, the queen, and the jack, and also 3 diamonds. So there's a total of 12 face cards. Okay. Okay, now, so let's start with the A part of the checkpoint. The probability, right? So we know the sample space is 52 because it's 52 total. So the probability of a queen, how many queens are there? There's 4 queens. There's 1 queen for each suit. The queen of clubs, the queen of spades, the queen of hearts, and the queen of diamonds, so it's going to be 4 over the sample space, right? So it's going to be 4 over 52. Now you get to reduce it. That's going to be 1 over 13. So this is a probability 1 out of 13 that when you draw a card, that it's going to be a queen. Okay. Now for B part, how about a diamond? If we notice, there's 13 cards of each suit. So there's 13 diamonds. So the number of diamonds is 13. The sample space is 52. So 13 over 52, right? Then we round off. We are reduced. So it's going to be 1/4. So 1/4 is the answer for B part. Now how about C part? It's going to be a red card. If we notice, right, there's 26 black cards and 26 red cards. So the number of red cards is 26 over the sample space, right, which is 52. So 26 over 52 is equal to 1/2. So that's the answer for part C. Now, part D. Part D says, what's the probability of having a face card or an ace? So here we know that there's face card or an ace, right? There's 12 face cards, right? Because there's 3 face cards for each suit, and there's 4 suits, so there's 12 face cards, and there's also 4 aces, right? There's one diamond of ace, 1 ace of hearts, ace of spades, ace of clubs, so there's 4 over the sample space, which is 52. So 12 plus 4 is 16 over 52. Then we reduce it. So the answer will be 4 out of 13. This is the answer for part D. Okay? Let me move on then. Okay, now. This is 8.3. This is called Basic Concepts of Probability. And this example comes straight from the book. Okay? This is called the addition rule for probabilities. For any event E and F from a sample space, from a sample space S, the probability of V union F is equal to the probability of V plus the probability of F minus the probability of V intersects F. So this is a formula that we're going to be using. Okay? Okay, now, example number 1. It says, when playing American roulette, a croupier, who is the attendant, spins a marble that lands in one of 38 slots in a revolving turntable, and there's there's a 38 slots. The slots are numbered 1 through 36, with 2 additional slots labeled 0 and 00 that are painted green. You see, there's a 00 and there's a 0. So these 2 are the green ones. Half, or the remaining slots, are colored red and half are black. So in other words, there's 18 red and 18 black. And there's also 2 green, a total of 38. Okay. Let's go here. The slots labeled 00 are not considered as even or odd. Now, here's my question, or the question that they're asking. Find the probability that the marble will land on a red or even number. Okay. So how are we going to go by that? Here's how we do it. Here's my solution. So we're going to let the set of red be R. So R stands for red. If I notice, I went all the way around, guys, and I counted all the red marbles, and these are the red slots, not marbles, the red slots that are painted red. You see, there's my 1, there's my 3, and so forth. I went all the way around, and these are all the red slots. Let the set of even be E. These are all my even numbers, right? Even, I went around the turntable, and like, for example, the 2, 4, 6, 8, 10 are black. You see, let me see where they're at. There's the 8, there's a 10, there's my 4, my 6, and my 2, right? Those are black. And the 12 through 18 are red, and 20 to 28 are black, and 30 to 36 are red. So the event E means that they're going to be even, okay? Because they want the marble will land on a red or even. Okay, now, here's where we apply the rule here. The probability of R union E, which means red or even, here's this total of 38. There's 18 black. There's 18 red, 18 black, 18 even, and 18 odd. Red and even are going to be 8. There's 8 that are red and even, right? There's these are red and even. So that's why there's 8. So the probability of V over N of S means there's going to be, my sample space will be what? 38, correct? Right, that's my sample space, 38. So the probability of red, there's 18. There's my 18 there. 18 over 38. Plus the probability of even, there's also 18 over 38. But then, guys, we have to subtract the ones that are red and even. So I'm going to subtract that one because this one's already counted up here. You see, that's why these, we don't count them twice because they're already counted up here. So in other words, I'm going to count these. There's 8. So it's going to be minus 8 over 38. So the answer is 28 over 38. We simplify. The answer is 14 over 19. So this is my answer. 14 out of 19 that this event will take place. The event that the marble will land on a red or an even. Okay. This requires, when I first did this in class, I had to, the class and I, we counted all the red ones and stuff like that. That's why this example is a good example to really understand, because this will be as hard as it gets for 8.3. Okay. Okay, now, by following the same process, example 2. Suppose 2 fair dice are rolled. Find each of the given probabilities. A part, the first die shows a 2, or the sum of the result is 6 or 7. Okay, now, for part A, we're going to use the same principle here. Let A represent the event that the first die shows a 2, right? So this is event A, and event B will be the result is 6 or 7. The sum is 6 or 7. Okay, so I like to have, these are all the possible outcomes here, right? This is my first die, this is my second die. So for event A, right, event A is right here, right, that the first die shows a 2, right? So this is my first die, right? It's a 2. You see, this is my first die, it's a 2. So that's why this is event A, right here, which is 1, 2, 3, 4, 5, 6. Like I said, my sample space is 36. And the event A is 6, right? Because this is event A and there's 6. Now, event B is a sum is 6 or 7, right? So all these, you see, this is a sum is 6, 6, 6, 6, and 6. And the ones here on the bottom are all 7. The sum is 7. So how many are there? There's 11. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So the probability of the event B is 11. Okay? Okay, now. So it's going to be 6 over 36, right? That's event A. Event B is going to be 11 over 36 minus the probability where A intersects B, right? Where these two intersect, right? So it's going to be these right here, right? This part is going to be there and there. So it's going to be minus 2 because there's 2 of them. So then, right, so then we do the 6 plus 11 minus 6 minus 2 is going to give us 15 over 36. We reduce it. The answer is 5 over 12. This is my answer. And it's always wise to have this picture, I mean, with you at all times. This picture's in the book, this sketch here. It's always nice to have access to it. Okay, because this way you can see exactly how it works. And all these guys, if you go diagonally, for example, these are equal to 2. These are equal to 3. These are equal to 4 and 5 and 6 and so forth, right? And 10 and 11 and 12. That's why if you go from corner to corner, that's where we get the sum of each one of 2, 3, 4, 5, all the way to 12. Okay, now for B part. Okay, the sum is 11, or the second die shows a 5. So again, my sample space is 36. There's my formula. So I'm going to let A represent the sum is 11, right? So 11 will be these two here. The sum is 11. It's going to be 2. And then let B represent the second die shows a 5. So this is my second die, right? This is my second die here, right? It shows a 5, which is 6. And a B is 6. Now, where do they intersect is right there. So it's going to be -1, right? So there's my formula. Plug everything in. -1/36. So the answer will be 7/36 is my final answer. Okay. Can I continue, guys? Please raise your hand up if you guys are okay. Okay, now, this is called the complement rule. For any event E, the complement means, it's the same thing as, this means complement, or you can say not E. It's the same thing. The probability of the complement of E is equal to 1 minus the probability of E. And the probability of E is equal to 1 minus the probability of the complement of E. Okay, now, odds in favor of an event are defined as a ratio of P of E to P of not E, or P of E over P of not E, or complement of E. And the complement of the probability of complement of E cannot be equal to 0. Okay, now let me show you real quick, guys, of the complement rule. Okay, in a way that can be understood before we go on. Hey guys, what if I tell you the probability that is going to, they say in the news that the probability of rain is 80%, right? And so 80% that there's going to be rain. So then what's the complement of that event? The complement means the probability that it's not going to rain. So the complement that that's going to rain is 80%. So the complement will be 20%, because 1 minus 80% will give you 20%. So the complement means not that event. I repeat, for example, the event of rain is 80%. So the complement of that event will be not 80%, which is 20%. Okay? Okay, now, so let's continue. So here's an observation, okay, of the odds in favor. The probability of E is equal to the number of E over the number of S, right, over the sample space, over the number of not the event E over the sample space. Hey guys, this, right, is my numerator. When you divide two fractions, this division becomes multiplication, and the second fraction, you flip it. If you notice, these will cancel to 1. So what's left? N of E over N of not E. So this is what we're going to be using. Okay? Let me show you the example. This is number 27 from page 434 from the book. Our marble is drawn from a box containing 3 yellow, 3 white, and 8 blue. Find the odds in favor in drawing a given marble. Right? So the odds in favor is going to be like this. Right? So part A, 3 yellow, 4 white, and 8 blue. Odds in favor in drawing a yellow means yellow over not yellow. Right? That's what we got over here, right? By the observation. So how many are yellow? Is 3. How many are not yellow? 4 plus 8, which is 3 over 12, which is equal to 1/4, or the ratio of 1 to 4. This is my answer. Okay? Look at B now. Odds in favor in drawing a blue marble. So it's going to be blue over not blue. The number of blue is 8. The number of not blue is 3 plus 4, which is 7. So the answer is 8 over 7, which is 8 to 7. This is the answer, the way they want the answer. This means 8 to 7. Okay, now for part C. The odds in favor in drawing a white. So it's going to be white over not white. So there's 4 white, and there's 8 plus 3, which is 11 that are not white. So what's the answer? 4 to 11. This is the answer that they're looking for. Okay. Okay, now this is for 47 to 54 on page 435. Okay, now it says data from the 2016 General Social Survey can allow us to estimate how many hours people who classified their work status as part-time or full-time actually worked in the last week. Use the following table to find the probabilities of the events. Okay, I'm going to do a few of these, maybe like about 5 or 6 of these. Let's start. Okay, this is the solution, right? So this is the formula that I'm going to be using. So the sample space is going to be 1591, 1591. So for every problem, that's my sample space. So for 47, a full-time worker, right? So a full-time worker is right here. So how many are a full-time worker? 1271. So the probability of that's going to be a full-time worker is going to be 1271 over 1591, which will be approximately, they want you to round off to about 4 places, 0.7989 is your answer. Okay. Now this is number 48. It's a part-time worker. So how many are part-time workers? Part-time workers is right here, right? So part-time workers is going to be 320. So the probability of the event of a part-time worker is going to be 320 over 1591, which will be approximately 0.2011. Okay, now number 49. Work 50 hours or more. So 50 hours or more, right, is here. So we go all the way down. It's going to be 393. So the probability of the event is going to be 393 over 1591, which approximately will be 0.2470. Number 50. Work between 0 to 19 hours, right? 0 to 19 hours is right here on the left, right? Is the first column, which will be 106. So the probability of the event is going to be 106 over 1591, which approximately is going to be 0.0666. Okay. Now, 51 through 54, a little bit more challenging, especially the last two. I'm going to do one of each, okay? On the next page here. Check this out. A part-time worker and someone who worked 40 hours or more. So again, the solution is still my sample space is going to be 1591. So here we go. A part-time worker and means intersection, right? So a part-time worker is here. A part-time worker and someone who worked 40 hours or more, right? So it's going to be a part-time worker and someone who worked 40 hours or more. So that's my event, right? So a part-time worker, which is this right here, and work 40 hours or more. So it's going to be 49 plus 21 because we're getting these from the part-time worker. And the and means who worked 40 hours or more, so it's going to be these two here. So it's going to be 70 over 1591, approximately 0.0440. Number 52 is done in the same manner. Now let me do because these two are the ands. Now let me do number 53 or number 54. Now here is where the or comes in. Okay? So for that, we're going to apply this formula here. Because this means or, the union means or, and this means and. So check this out. The probability, this is how we get the answer, okay? But let me show you how. Because the probability of a part-time worker, right? Part-time worker is going to be 320. So I have to add 320 there. And then 29 hours or less. So it's going to be these two here, right? 20 hours or less are going to be 106 plus 129. But minus these two here. Why? Because these two I already added with the part-time workers. So I don't want to count them twice. That's why I subtract them. Okay? Now, let me explain it more in detail here. So we're going to let A represent part-time workers. Right? So part-time workers and B represent 20 hours or less. So part-time workers, right, are 320. The ones that work 20 hours or less is 106, right? Is because 20 hours or less can be from 0 to 29 hours, which is 106 plus 129. That's my N of B, right? Which is a number of the people who work 20 hours or less. But then minus, right? Where do these two intersect? They intersect here, right? Because this is the part-time workers, and these two here, that's where they intersect. So that's why we subtract 77 plus 87. So the answer will be 391. So it's going to be 391 over 1,591, which approximately is equal to 0.2458. And again, this is as hard as it gets, not number 54. Okay, by applying the rule here, this rule makes it a little bit more easier. There's some students that can actually get the answer without doing, the formula. They just go here. Part-time worker is 320, right? So it'll be 320, and then workers that work between 0 to 29 hours is going to be 129 plus 106. So I'm going to add all these right here, which is 320, and then plus these two here. You get the same answer. Okay? Because these, they've already been counted right here. So the answer will be 29 plus 42 plus 320. That will be the answer also. Okay, so there's different ways to get the answer, but this is helpful to do it with a formula. Okay, now we're doing 9.2. This is multiplication principle, permutations and combinations. So the multiplication principle is like this. Suppose you have n number of choices, and choices must be made with m1 ways to make choice 1, and m2 ways to make choice 2, mn ways to make choice n, and so what you do, guys, all you do is multiply each possible way. So it'll be m1 times m2 times m3 and so forth until I get to mn. This is different ways to make the entire sequence of the choice, or the choices. Now, this can be a little bit hard to understand, but let me show you how the multiplication principle actually works with an example. This is number 24 on page 477. It says here, how many different heating units are possible if a landowner has 3 choices for the efficiency ratings of the furnace, 3 options for the fan speed, and 6 options for the air condenser. So how many different coolings are there? Right, so number of choices for efficiency rating, which is 3. The number of choices for the fan speed, which is also 3. And the options of the air condenser, which is 6. So it's going to be 3 times 3 times 6, which is 54. That's where you apply the multiplication principle. 54 different units are possible. Okay, now this is number 28 on page 477. It says here, the United Postal Service currently uses 5-digit zip codes in most areas. How many zip codes are possible if there are not restrictions on the digits used? But restrictions means there's no restriction, so the numbers can repeat and everything. Okay, but how many? Okay, so that's the first part. The second part, how many would be possible if the first number could not be a 0? So solution, no, 10 digits make all the numbers, right? From 0 to 9 makes all the numbers. These are called the digits. So for part 1, which is how many zip codes are possible if there are not restrictions on the digits used, how many can go in the first slot? It's going to be 10, 10, 10, 10, and 10, right? Because there's no restrictions. You multiply them out. So the answer is 100,000. Now for the second part, how many would be possible if the first number could not be a 0? So first number cannot be a 0, right? So 9 can go here, right? Because 0 cannot go in there. So how many are left? Are 9 digits, 1 through 9. And then 10, and 10, and 10, and 10. We multiply it out. It's going to give us 90,000. So 90,000 possible ways. Okay, now this is number 30 on the same page. For many years, the state of California used 3 letters followed by 3 digits on its automobile license plates. Okay. So note, 26 letters are in the alphabet and 10 digits make all the numbers. How many different license plates are possible with the arrangement? So these are my 3 letters followed by my 3 digits. So there's no restriction. So 26, 26, 26, right? And the digits will be 10, 10, and 10. So the answer will be, multiply it out, you're going to get something like 17,576,000. That's how many ways, possible arrangements. Now for part B, when the state ran out of new numbers, the order was reversed to 3 digits followed by 3 letters. How many new license plate numbers were then possible? So we switch the order, digits and letters. So again, it's going to be 10 times 10 times 10, and 26 times 26 times 26. And here, guys, it doesn't matter the order, so we get the same result. Okay, which is 17,576,000. Then part C, several it says here, several years later, several years ago, the number described in part B were also used up. The state then issued plates with 1 letter followed by 3 digits and 3 letters. How many new license plate numbers will be arranged provided? Right, so that's my new letter. Oh, fuss. What did I do here? Hold on, guys. Here we go. There's my letter. There's my digits. I think someone's in the program. And there's my letters, right? So it's going to be 26 letters, 10 digits, right, on each slot. And then also 26 letters, and 26 letters for each slot. So we multiply it out, and we get something like 456,176,000. Those are the possible arrangements. Okay? Okay, now we're going to cover factorial. Okay, and again, guys, I'm just going giving you guys enough information that you guys can actually do some of the homework, because these are long sections, and I don't want to waste too much time, right? Because I don't want to run out of time. So I'm trying to give you enough information, the most important information, so you guys will be able to do the homework. Okay? N factorial. For any natural number n, this is a formula for n factorial. It's going to be n minus 1, n minus 2, n minus 3, and so forth until you get to 1. And by definition, 0 factorial is equal to 1. Okay, let me show an example here. Evaluate 4 factorial. By using the formula, right, so we're going to go all the way from 4 and declining all the way till we get to 1. So it's going to be 4 times 3 times 2 times 1, and then we multiply them out, and that's my answer. For B part, 6 factorial. 6 times 5 times 4 times 3 times 2 times 1 equals to 720. 1 factorial will just be 1. Now D part, 6 factorial divided by 4 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. So we can begin to cancel some of the numbers there. 1 over 1 is 1. 2 over 2 is 1. 3 over 3 is 1. 4 over 4 is 1. So we're left with 30 over 1, which is 30. So that's my answer. Now comes permutations. A permutation of set of elements is an ordering of the elements. For instance, there are 6 permutations ordering of the letters A, B, and C, namely. Here, for example, these are the possible combinations that you can get and see, right? 3 letters in 6 different orders, right? 1, 2, 3, 4, 5, 6. For example, here, guys, the order matters. For example, ABC and CBA are 2 different orders. Okay. Okay, now example 3. How many batting orders are possible for a 9-person baseball team? Okay. So solution, there are 9 possible choices for the first batter, 8 possible choices for the second batter, and so forth. So for example, it's going to be 9 times 8 times 7 times 6, right? Because nine players can actually bat first. Then after 1 is chosen, then 8 players can bat second, and then that player cannot bat again, right? Until it's turn again, and then it's going to be 7 and 6 all the way till we get to 1. So the answer is B, 362,880. Or you can do 9 factorial. It's the same thing, which is the same answer, 362,880. Okay, now comes the definition of permutation. Permutation is if n PR, where n is more than r, is the number of permutations of n elements taken r at a time. Here, guys, the order does matter, and here's my formula. But the order matters. Okay, now let's say I have 3 letters, A, B, and C. I would like to know how many 2-letter arrangements are possible. And remember, order matters. So how many ways can I get 2 letters out of the 3? So it can be AB, right? Or BA, right? Because here the order matters. AB and BA are 2 different orders. Or it can be AC and CA, and it can be BC and CB. And that's all the possible ways I can get that type of arrangement. So it's 6 possible arrangements. Now let's do it by using the formula, right? So it's going to be 3 permutation 2, which means, right, this is my n is a 3 and my r is my 2. So n factorial will be 3 factorial over n minus r factorial will be 3 factorial over 3 minus 2 factorial, which will be 3 factorial over 1 factorial. It'll be 3 times 2 times 1 over 1, which will be 6. That's how you use the formula. This, you can also plug it into the calculator, right? If you don't know how, just Google permutations and combinations, how to input into the calculator, and input your type of calculator, and it can show you how to put that in there. Or it can be, you have write 3 letters and you want 2 arrangements, so there's about 2 arrangements. How many letters can go here, right? It can be 3 because A, B, and C can go first. After you after you choose the letter A, how many can go here? How many are left? 2. So 3 times 2 is 6, right? You can do it also this way. Okay, now this is number 40 on page 478. It says from a cooler with 8 cans of different kinds of soda, 3 are selected for 3 people, and how many ways can this be done? So by using the formula, we have 8 permutation 3, which will be 8 factorial over 5 factorial, right? So here we stop at 5 factorial, that way they can cancel. That's equal to 1. So we're left with 8 times 7 times 6, is the answer is 336. So there's 336 possible arrangements. Now, let me do it another way, right? You have 8 cans and you want arrangements of 3s. Of 3s, right? So we're going to put 1, 2, 3, right? These are the arrangements. How many can go here? 8. Then, right, then after you choose 1, right, so there's going to be 7 left. And then after you choose another one, there's going to be 6 left. So this is my answer, 8 times 7 times 6. And if you notice, that's what I got up here. The answer is 336. Only for permutations, you can do it in 2 ways. For combinations, you can't. Okay, which that's the next thing that I'm going to cover. Combinations. For combinations, this is my formula, and the order does not matter. For example, let's do the same example that I did earlier for permutations, right? When I have 3 letters, A, B, and C, and I would like to know how many 2-letter groups are possible. Remember, order does not matter. So it can be AB, it can be AC, and it can be BC, right? Because AB and BA are the same one. Order does not matter, so it's only 3. Now, let's plug into the formula. Let's see if it's true. So it's going to be 3 factorial over 2 factorial, because that's my R, times 3 minus 2 factorial. So we got 3 factorial over 2 factorial times 1 factorial. This will be the same thing as 3 times 2 times 1. 2 factorial is 2 times 1. 1 factorial is just 1. So here, guys, those cancel. So we're left with 3 over 1. The answer will be 3, right? So the answer is 3. Now, let's do number 46 on page 478. It says here, 4 items are to be randomly selected from the first 25 items on an assembly line in order to determine the defect rate. How many different samples of 4 items can be chosen? So what's the answer? 25 combination 4. Right? And this is my result. Right? Because 4 times 3 times 2 is 12. That's 12 times 2. Right? So there's a 2. Let me go back here. Previous. Here, guys, right? So 4 times 3 times 2 is 24. That's why I cancel that with all these right here. So I'm left with 25 times 23 times 22, which is 12,650. Okay. Okay, now, to sum up permutations and combinations. Different orderings of an arrangement of the art objects are different permutations, right? Here are the clues when it's going to be a permutation. Arrangement, schedule, order or order matters. These are the key words for permutation. The key words for combination: group, committee, set, sample. Order does not matter. These are all clue words for combinations. Okay. Okay, now this is number 59 on page 478. It says here, a lottery game requires that you pick 6 different. I forgot to put here 6 different numbers. I forgot to put numbers there. That you pick 6 different numbers from 1 to 99. If you pick all 6 winning numbers, you win $4 million. How many ways are there to choose 6 numbers if order is not important? So here, guys, that's going to be, right, for A part, order is not important, is going to be a combination. So it's going to be 99 combination 6, and then you plug that in the calculator, it's going to give you something like 1,120,529,256. And for part B, right, order matters, so that's a sign of permutation. So 99 permutation 6, which will give you 806,781,064,320. Okay, by using the keywords there. Okay, now this is number 60 on page 479. It says in exercise 59, you pick 5 out of 6 numbers correctly, you win 5,000. And how many ways can you pick exactly 5 of the 6 winning numbers without regard to order? Which means I'm going to use a combination. Okay? So first of all, 5 out of 6, right? So it's going to be 5 out of 6 means 6 combination 5 for this part here. To pick 5 out of 6. Okay, now, remember the lottery requirements need to pick 6 numbers from 99. So here it is, right? So I need to pick one more, right? Because say I pick 6 numbers, right? Out of 99, so then there's 93 left. And say to win the 5,000, if you get 5 right, it's 5 out of 6, so I need to pick one more. So in other words, I need to pick one more out of the 93, which means times 93 combination 1. And this is what I tell my students, this is key here, guys, for these type of problems. And we notice, right, that's my 99, so this must equal to 99. That's equal to 6, so these must equal to 6. The outer must equal to 6, and the ones to the left must be 99. So 6 combination 5 is 6. 93 combination 1 is 93. So 6 times 93 will give you 558. So that's your answer. This is number 58. I believe this will be the last one. Okay. It says a financial advisor offers 8 mutual funds in the high risk category, 7 in the moderate risk category, and 10 in the low risk category. An investor decides to invest 3 high risk funds, 4 moderate risk funds, and 3 low risk funds. How many ways can the investor do this? Okay. If you read the problem carefully, order does not matter, so it's going to be combination. So 8 mutual funds, right? We want 3, so that's going to be invest 3 from the 8 High risk is going to be 8 combination 3. 7 moderate risk, and we want 4. So 4 from the 7 is going to be 7 combination 4. And 10 in low risk, and we want 3. So invest 3 from the 10 is going to be 10 combination 3. So 8 combination 3 is 56. 7 combination 4 is 35. And 10 combination 3 is give us 120. So if we multiply those out, it's going to give us 235,200. So that's how many ways you can select, an investor can select the funds. Okay? Hey guys, that's it for this PowerPoint. I'm happy that I was able to present it. And if you need a copy of this PowerPoint, just send me an email at aesasi@epc.edu, and I'll be more than happy to send you a copy of this PowerPoint. Okay. Thank you.
Thank you, Mr. Azasi. Is there any questions for Mr. Azasi before we leave today? All right, no questions. So next week we won't be coming in because we have Thanksgiving, and we would like to wish you all a very happy Thanksgiving. But there is one more TVE left for the semester. On December 3rd, we'll be having EPCC Culinary Arts at 1 p.m. And then for Math Happy Hour, we'll be going over the final exam reviews for both Math 1314 and Math 1324. I would like to thank you all for coming today, and I hope that you have a wonderful Thanksgiving.